Hi everyone, and welcome to this new video of Math Puzzle with Q. The new puzzle we are going to solve today is about finding the general formula of the quantity x to the power of n plus y to the power of n when you already know the value of the sum x plus y and x squared plus y squared. So in this video we are going to see that we can approach this problem via two angles. So the first step of this puzzle will be to find this general formula regardless of the value of n. And the second step of this problem will be to identify some condition in which you can guarantee that the x to the power of n plus y to the power of n will either always be a rational number or always be an integer number. So that's what we are going to work on today. So today the new problem we are going to see is the following one. So we have x plus y that is equal to 1 and x squared plus y squared that is equal to 2. And so the question we're going to try to answer today is to try to find a general formula for xn plus yn. So the thing we're going to do first is to call this quantity Sn. So we can call this S2 and this is equal to S1. Okay. So the first thing that we're going to do, and that is going to help us in the future, is to actually try to find the value of the product x multiplied by y. So we are going to call it P equal xy. And we are going to see if we can find already the value of xy based on the value of S1 and S2. So one thing that we can notice is that if we take S1 and we square it, we have x plus y squared, which is equal to x squared plus 2xy plus y squared. And so this is equal to S2, because we have x squared plus y squared, plus 2 times the product. So at the end, we have 2 times the product that is equal to S1 squared minus S2. And this is equal to 1 squared minus 2. So this is equal to minus 1. So at the end, we have a P, which is xy, that is equal to minus 1 over 2. So now what we're going to do is to use the same trick we used to find the value of P, and use that trick to find the value of S3, S4, S5, etc. So let's do that right now. So we have x plus y to the power of 3, that is equal to, so if you remember Pascal triangle, you will know that you can have this formula, which is x to the power of 3 plus 3x squared y plus 3x y squared plus y to the power of 3. Now we are going to group the similar power together. So we have x to the power of 3 plus y to the power of 3. So this is exactly S3. And now what we can see is that for the two terms here and there, we have in common the product xy that is equal to P. So we can write this as 3xy x plus y. So this is equal to S3 plus 3p S1. And we know that x plus y is equal to 1, so x plus y to the power 3 is equal to 1 to the power 3, which is just equal to 1. So at the end we have S3 that is equal to 1 minus 3p S1. So we have S3 that is equal to 1 minus 3 multiplied by minus 1 over 2 multiplied by S1 that is equal to 1. So this is equal to 1 so we have plus 3 over 2 multiplied by 1, so we have 5 over 2. And so this is the value of S3. Okay, let's continue this way for S4. So we can write that x plus y to the power of 4 is equal to x to the power of 4 plus 4x to the power 3y plus 6x squared y squared plus 4x y cubed plus y to the power 4. So we are going to do the same grouping as before, and we have x to the power 4 plus y to the power 4 plus 4xy x square plus y square plus 6xy square. This is equal to S4, what we are trying to find, plus 4 multiplied by p S2 plus 6 multiplied by p squared. So it's easy to see that S4 is equal to x plus y to the power 4, so this again is equal to 1, so we have S4 is equal to 1 minus 4ps2 minus 6p squared. So this is equal to 1 minus 4 multiplied by minus 1/2. S2 is equal to 2 minus 6 multiplied by 1/2 square. So this is equal to 1 plus 4 minus 1/2 square is 1/4 multiplied by 6. So we have minus 6 over 4. This is equal to 5 minus 3 over 2, which is equal to 7 over 2. And this is what S4 is equal to. So it looks like we are doing a good job of finding the value of Sn based on the value of Sn minus 1 and minus 2, etc. As you can see, to find the value of S3 here, we use the value of P and S1. And in order to find the value of S4, we use the value of S2 and P squared. So now let's try to find the general formula of Sn. So what we're going to write is that x plus y to the power of n, we're going to use the formula of the binomial theorem in order to find the value of x plus y to the power of n. So first of all, I want to remind everyone that this is obviously equal to s1 to the power of n, that is exactly equal to 1. But this is also equal to x to the power of n plus n choose 1 x to the power of n minus 1 y plus n choose 2 x to the power of n minus 2 y square plus etc. plus n choose n minus 2 x square y n minus 2 plus n choose n minus 1 x y power n minus 1 plus y to the power of n. This is equal to x to the power of n plus y to the power of n, which is exactly equal to Sn, plus n choose 1 xy x to the power of n minus 2 plus n choose 2 xy square x to the power of n minus 4 plus etc. plus n choose n minus 2 xy square y to the power of n minus 4 plus n choose n minus 1 xy y to the power of n minus 2 plus plus nothing because we already have the y to the power of n here. But what you can see is that we have this element that goes with that element and this element that goes with that one. So we can do some pair of elements and we have equal to Sn plus n choose 1 product p x to the power of n minus 2 plus y to the power of n minus 2 plus n choose 2 p square x to the power of n minus 4 plus y to the power of n minus 4 plus etc. etc. So now you may wonder what is the last term of this formula. Well, it will depend whether n is even or odd, but you can verify by yourself that this formula can be written as Sn plus n choose 1 p s n minus 2 plus n choose 2 p square s n minus 4 plus ... plus, and here the two options are n choose n divided by 2 p to the power of n divided by 2 if n is even, and if n is not even we will have n choose n plus 1 divided by 2 p to the power of n minus 1 divided by 2 x plus y that is also equal to S1 if n is odd. So at the end, this formula is giving us a nice recursive way to calculate the next element of Sn based on the other element Sn-2, Sn-4, etc. But you may ask, is it useful? So it is useful if you want to calculate the Sn recursively, but the problem is this formula doesn't really give you directly a nice way to calculate the Sn. Using this formula, you can only find S3, S4, S5, etc. one element at a time, and it's not giving us directly a formula that says Sn is equal to that, whatever the value of n is. So the question now is there a way to know this general formula for Sn? Well, actually there is. So now, instead of trying to solve this problem using the induction approach, what we are going to do is instead try to solve the problem using a geometrical approach. So let's recall the two equations that we had, which are S1 equal x plus y that is equal to 1, and S2 that is equal to x squared plus y squared that is equal to 2. So here what we are going to do is to represent these two equations in the graph of x and y. So here we have the x, here we have the y. And first of all, the equation x plus y is nothing else than a line that is having a slope of -1. So the line is going to look like this. And we know that when x equals 0, we have y equal 1. And when y equals 0, we have x equal 1. So basically the line is going to cross the x-axis at x equal 1 and the y-axis at y equal 1. Okay, so now the equation x squared plus y squared equal 2 is nothing else than the equation of a circle of radius square root of 2. X squared plus y squared equal r squared is the equation of a circle of radius r. So we can draw this circle that will look more or less like this. And we know that this circle is crossing the x and y axis at the value square root of 2 and square root of 2. Okay, so basically for the x and y variable to verify this equation, the only way that it can happen is that the x and y coordinate can only be both on the circle and on the line, and we can see that in that case it happens in only 2 points that are located here and there. So let's try to find a coordinate x and y, and to do that we are going to use a complex number. So the solution can be noted x plus I y, And because the solution is located on the circle of radius square root of 2, we can note that this is equal to square root of 2 e to the power of I theta. So as you can see, we already know the radius square root of 2. The missing parameter here is the angle theta. So here, maybe to be a bit more general and to see when solution actually exists, we are going to use, instead of using the value of 1 and 2 that are right here, we are going to use the general value of S1 and S2 to see in which case this set of equation actually has a solution and how many of them we have. So in the general case, what we have is that this circle has a value of square root of S2. So instead of 1 here, the value of the intersection of the line to the two axes will be equal to S1 here and S1 there. So now let's imagine that we are moving this line here in the upper right corner by increasing the value of S1. There will be a moment where this line is going to barely touch the circle, after which point the set of equation will no longer have any solution. So let's find this extreme case. This is when the line is going to be located like this and is going to touch this point of the circle. At this point, what we're going to have is a right triangle that we can draw like this, where the right angle is located here. And we know that this length is equal to S1, and this length over there is equal to the square root of S2. So according to the Pythagorean formula, we know that square root of S2 square plus square root of S2 square must be equal to S1 square, which means that we have 2S2 that is equal to S1 square. And this is a case where we have only one solution, and this solution is located right here. When S1 square is strictly lower than 2S2, then we are going to have exactly two solutions. And when S1 square is strictly greater than 2S2, then there is no solution. So in our current case study, we have S1 square that is equal to 1 square, which is equal to 1, and 2S2 that is equal to 2 multiplied by 2, that is equal to 4. So in that particular case, it is obvious that S1 square is strictly lower than 2S2. So we do have two solutions in that case that we are going to calculate. So let's try to find this value of x and y for these two solutions. So what we know about x and y is that we have x plus y that is equal to S1. And we also know that x is equal to square root of S2 cosine theta, and y is equal to square root of S2 sine theta. So we can write that S1 is equal to the square root of S2 multiplied by cosine theta plus sine theta. And if you check your trig formula, you know that this is equal to the square root of 2 of cosine theta minus pi over 4. So in other words, we have the cosine of theta minus pi over 4 that is equal to S1 divided by the square root of 2S2. In other words, we have theta that is equal to pi over 4 plus or minus arc cosine of S1 divided by the square root of 2S2. And this plus or minus value actually represent the two possible solutions. If we were at the extreme case when we have 2S2 that is equal to S1 square, this value would be equal to 1, and arc cosine of 1 is equal to 0. So in that case, plus or minus 0 will be the same solution, which would be theta equal pi over 4. Okay, so we can conclude that the two solutions for x and y are x equal square root of s2 cosine of pi over 4 plus or minus arc cosine of s1 square root of 2s2, and y equal to the square root of s2 sine of pi over 4 plus or minus arc cosine of s1 divided by the square root of 2s2. So now we are basically done, because when we want to know what is x to the power of n plus y to the power of n, we just have to elevate this to the power of n here and there, here and there, and we can simply write x to the power of n plus y to the power of n equal, and we have our formula. So in the specific case of that video, we have s1 that is equal to 1, s2 that is equal to 2, s1 divided by the square root of 2s2 that is equal to 1 divided by the square root of 4, which is equal to 1 over 2. The arc cosine of 1 over 2 is equal to pi over 3. So we have x is equal to the square root of 2 cosine of pi over 4 plus or minus pi over 3, y equal square root of 2 sine of pi over 4 plus or minus pi over 3. Now, if you enter this value in your machine for the case, for example, plus here, then you are going to have a value of x that is equal more or less to minus 0.366, and a value for y that is more or less equal to 1.366. And when you do x plus y, you will have this that is equal to 1, which is the value of s1. But interestingly, when you take x to the power of n plus y to the power of n, you would have for n equal to a value of, if we go back to the previous solution that we found, so for a value of 2, it will be equal to 2. For n equal 3, this value is going to be equal to 5 over 2. And for the value of 4, you would have s4 that is equal to 7 over 2. So what is interesting here is that although we have very irrational number for the value of x and y, the value of xn plus yn seem to be always rational value. And we can actually prove by induction that for any value of n, x to the power of n plus y to the power of n will be a rational number. So how do we actually prove this? Well, it's actually very easy using the induction formula that we found above. So let's go back to the induction formula that we found right here. So what we saw here is that we can always express Sn as something that depends to x plus y to the power of n and previous value of Sn, which are Sn minus 2, Sn minus 4, etc. So we have Sn that can be expressed as x plus y to the power of n plus a sum and product of value that are only depending on p and previous occurrence of sk. So for example, Sn minus 2, Sn minus 4, and other integer number. And we know that the sum and product of rational number is a rational number. So as long as p is a rational number and the previous occurrence of sk are rational number, then Sn will be a rational number. And actually, we also know that the sum and product of integer is also an integer. So in the specific case where we can guarantee that p is also an integer and s1 and s2 are integer, then Sn will always be an integer. So in our case, what we saw is that p is actually equal to -1/2, which is why the xn plus yn is not always an integer. But if we can guarantee that p is an integer as well as s1 and s2, then all the value of xn plus yn will be an integer. So let's see a quick example of that case right now. So let's say that we have s1 that is equal to 1 and s2 that is equal to 3. We still have the property that s1 square that is equal to 1 is strictly lower than 2s2 that is equal to 6. So we know that we will have always two solutions. And on top of that, we have x plus y square that is equal to s1 square and is also equal to x square plus y square plus 2 times xy is equal to s2 square plus 2p. So we have p that is equal to s1 square minus, it should be only s2, s1 square minus s2 divided by 2. That is equal to 1 minus 3 divided by 2. So this is equal to -1. So p in that case is an integer. So is s1 and so is s2. Using the formula above, we can write that x is equal to the square root of 3 cosine of pi over 4. Let's say that we choose plus arc cosine of s1 divided by the square root of 2s2. So this ratio is equal to 1 divided by the square root of 6. And so the arc cos of 1 over the square root of 6 is not something that can be easily expressed in terms of pi. We have y that is equal to the square root of 3 of sine pi over 4 plus arc cosine of 1 divided by the square root of 6. And you can enter those numbers in your machine and you will have a number that is not a rational number, let alone an integer. Even when you take the power of n, same for y to the power of n. But interestingly, when you take x plus y, x square plus y square, x cubed plus y cubed, and x to the power of 4 plus y to the power of 4, this number will have integer value. So we'll have 1 for x plus y, 3 for x squared plus y squared. And if you keep moving in the power, you will find that x to the power 3 plus y to the power 3 is equal to 4. X to the power 4 plus y to the power 4 is equal to 7, etc. So what is interesting here is that even though using geometry, we can find the exact value of x and y, and so we can deduce what is the exact value of x to the power of n plus y to the power of n. At least we have an exact formula. From this formula, it is not immediate that this number can sometime always be integer. But thanks to the induction formula, we can actually prove that for any value of n, this number will be an integer value. That's all for this video. If you want to see more videos like that, please feel free to let me know in the comment.